Okay, so today we're going to be solving the smallest subtree with all the deepest nodes. I have actually solved this problem before, but it's been a while, so I'm going to retry this. Given the root of a binary tree, the depth of each node is the shortest distance to the root. So the shortest distance to the root from here, this would be 1. So the depth here is 1. Depth here, I guess, is 0 because the distance of the root to itself is 0. And a node is called the deepest if it has the largest possible depth amongst any node in the tree. So in this example, these two nodes are the deepest, but it's not always the case that these two nodes will be the deepest, like two nodes, or you could have one node. And if 7 and 4 didn't exist, then the deepest nodes would all be these, which all have the depth of 2. We're looking for the parent node that has, I guess, the subtree that has all of the deepest nodes. In this case, it's the parent of 7 and 4, 2, but it's not always the case that's going to be the parent of the deepest nodes because let's say 7 and 4 did not exist, then you would have 6, 2, 0, 8. Those 4 would be the deepest nodes, and then like it wouldn't be 5 or 1. It would have to be 3 because 3 is the only thing that contains all 4 of these nodes in a subtree. And that is the root of the tree. So immediately we know we have to figure out the depth of nodes in some way. And since this is a tree problem, we could solve this by breadth first search, where we look at each level. It's a little bit convoluted, but I think it's doable to do it that way. It might be easier to first start out with a depth first search solution recursively, as those can be a little bit easier to code. So we know we have to keep track of the depth of a node somehow. Maybe we might want to be passing like the depth of a node upwards or downwards somehow, either in a function signature or in the return. Excuse me, I'm going to cough. And then, so now we need some kind of depth first search function that takes in a node. And we probably want that to, I'll say we can return a depth or some kind of marking of whatever depth can be. And then maybe let's say a node itself would be something kind of natural to return, since we need to return a node in the outside of the function to return to satisfy our requirements. So we have some kind of depth first search that we need to do, and that is going to return a node and a depth. Which node do we want to return? That's what we need to calculate now. So the logic behind determining which node, we probably need the max of something. So max depth, actually, of left, right. So let's say you're here, 5, and you want to return something that has the maximum depth out of the left and right. We want to return this 2 node here, actually. But before we even get there, we know that like if we're here, we'd maybe return 1 for the depth. Let's just say that upwards here to 2. Or we can return 0. Let's see. We'll talk about maybe our base case. So base case would be if no node. So your base case would actually not be here. It would be like if you're a child of this. Return none and 0. That kind of makes sense. Then now when we're here at the 7 or we're here at the 4, what should return? Well, in this case, the depth of the left and right are going to be equal. So there's another case here. Left depth equal to right depth. There's going to be 3 cases. So we know now there's like either your left has the deepest node, like here 3, 5, 2, 7, 4, your right has the deepest node, or the depth of your left and right are going to be equal. Those are three cases that we need to consider. And what we return actually is going to depend on which one is the max. So max depth, actually. So left and right, those are kind of, I think, obvious. If you're here at 5, the right has the deepest node, so you're going to return whatever is the right here. And similarly for the left, that's just going to be the same kind of situation. But what if your left and right depths are equal to each other? In that case, the example here is like 2. 7 and 4 are going to be equal to each other. And so in that case, you'd actually want to return the node itself that has the equal left and rights, given that that's probably the deepest. Like left and right depths are deepest. You'll see, like, let's say if you had something equal like here, 1 and 0, that would have to probably compete against this at some point. But since we're maybe adding 1 to the depth as we pass it upwards, I haven't shown that yet, but that's what part of what we'll be returning, it's the depth. Then maybe this depth here would be 1, this depth here would be 2, this depth here would be 3. And then when you get to here, this is where you're going to be comparing left and right. And this depth is 1, this depth is 2. So 3 and 2, you'll be returning whatever's on the left, right? So that kind of gives us enough information to start coding this. We can make a function called depth first search that takes in a node, and then we don't really need anything defined yet, so we can just start writing out the function. And so it's actually going to be returning, let's say, like an object or a dictionary. So if we have our base case, so if not node, then maybe we'll return an object like this, where we have node and depth. And then our node, we'd want that to be equal to none. Our depth would equal to 0. That takes care of our base case. Now, next we need to compare the left and right. How we compare that left and right is going to be with recursion. So we can write down like L, that's going to be equal to depth first search of node.left, and right is equal to depth first search of node.right. And now we compare if L dot, and we're assuming that we're going to be returning some object here that has values node and depth, keys node and depth, sorry, I mean. So if L.depth is greater than R.depth, what we want to return is going to be return the node we want to return is L.node, and then the depth we want to return is L.depth plus 1. Next, we can kind of just switch this around. Actually, the easiest way to do this would just be to change this here, to less than. And so you would actually, I have this label as L, but this would be node. And then this here also would be node. This would be R now. This would also be R. And then finally we have our third case where they're going to be equal to each other. In that case, we want to return the current node. So node, a little bit confusing here, but we'll be returning no node. And then the depth would be either L or R depth, because they're going to be equal. And we're going to add 1 to it. Now, next we see we need to run this operation. So we'll do DFS giving the root. And then we'll store that in like some kind of intermediary variable called answer. And we want to return answer.node. So let's see if that works. I shouldn't be clicking this so quickly, but okay, depth is not defined. So apologies for the cut, but what I was trying to show earlier with the node.left, node.right, and then l.depth, r.depth, the way that you do that is by creating a class to hold your result. This is similar to a struct in many other languages. Okay. Should just be able to return something like this in Python. Node depth equals 0. But since we're getting this not defined error, we'll call this return object, and then depth versus node.left, node.right. So here we maybe do something like object node equals l.node, object.depth equals l.depth plus 1, and return object. And similar here, change this to R, and here node equals node, object.depth equals l.depth plus 1, return object. Now let's see if this works. Syntax error after dictionary key. Colon expected. Yeah, I just needed to make that into a colon instead. Depth is not defined. I'm probably mixing together Python and JavaScript here. Let me just take a moment to debug. Equals 0, and we'll just kind of change this to an empty dictionary. Try this again. Take this to attribute depth. So object has a node and depth that we're returning here. Left, right, l.depth greater than r.depth. Go to printing, none and depth. Now this is a little bit strange. (23) and 25. Print L. Yeah, we have node and we have depth. So it says that dictionary is not having depth. One thing I can do to fix this real quick is to just not use a dictionary, but I think we can return this just as a tuple and then take the index, which is how I've solved this in the past, I believe. So we can return none and 0, and then pfs node.left, node.right, l.depth, r.depth. So you see that the depth is actually the first, no, it's number 1 index, not the first. This here will be also index 1, and we will return L0, that's the node. L1 is the depth, plus 1. Similarly here, it would be R0, R1 plus 1. Return node with L of 1 plus 1. And here, instead of returning answer.node, we return to answer. We're not returning depth, we're returning node itself, so answer of 0. Oh, great. Forgot to change this. So we're looking at L1 is less than R1. So now we have the cases are being accepted. We have coded this right. I had to go back and look in the Python documentation to find out how to return an object like that, because it's not the same as in JavaScript. But we have this going on, and looks like it generates the correct answer. There's some edge cases. Maybe we should see if there's no nodes at all, you just get an empty tree, what would happen? In that case, you'd have differs from none, and return 0 and none. So that's kind of what is expected. If you have just one node, then you still get 0, 0 here, and then you get to the case where they're equal to each other. So then you just return the root node. The root node contains all the deepest nodes. So that, I guess, is what is expected. But I think if you look at the edge cases here, say you will have at least one node, and then values. Values being negative doesn't really affect anything, so it doesn't really matter what they have here. And values of nodes and trees being unique also doesn't really affect anything, so we don't really care if they're unique or not. So to cap it off, I guess the time complexity of this, in a worst case scenario, you're going to have a tree that maybe is not balanced. It's just like a straight line, like a linked list. Then that time complexity would be O of n with a really, really unbalanced tree. And then the node that has all the deepest nodes, that would probably be like, the second to last node has like the last node in it in terms of like the depth. So if you had like 3, 5, 2, 4, then that would be like 2. So that's O of n in the worst case, if you don't really have a tree. On the average case, if the tree is balanced, then that would be O of n log n. You would only, I guess, you go down to like the left side, but then you pop back up here. Okay, that's actually a memory complexity. In the worst case, it would always just be O of n, actually, no matter how the tree is distributed, because you would have to check all paths in a tree. That's the kind of algorithm that this is. So let's try submitting this now and see. We have cleared all the edge cases, so that's good. And that seems to be a correct solution that kind of gets us in the optimal distribution. The ways to optimize this, I don't really think there's any, unless the call stack space, that is actually the O of n log n that was talking about, because if it's a balanced tree, then it would be n log n, and if it's an unbalanced tree, then the memory complexity would be O of n due to call stack size. So I hope this solution was informative to you. Don't be like me and try to use up like some strange, like returning an object if you're not familiar with it. There is a way to do this, but you had to like define like a type or a class, and then I think that's what I probably should have done. Just define a class, kind of like a struct in Go or some other language. But if you're just working with some simple thing like this, It's probably okay. If you really want these variables to be named, then like instead of doing L like this, you can do something like L node and L depth, because you're unpacking a tuple. But anyways, that's probably what I should have done to make this simpler. Anyways, I hope you enjoyed this. I know my videos have been taking around like 20 minutes per solution. I'd hope to try to make this a little bit faster as I get better at this. So thanks for watching, and hope to see you guys again.